Are we live?
We are live. Though we have no proof.
No, actually.
Simulations.
And the lower you go in analyzing what matter is, the more empty space you actually find.
Right.
So, it's like you could almost argue, and some people do, that, I mean, we say there's this thing called mass, right? And mass is what proves there must be matter.
Right.
Because we can measure it.
And there's resting mass and other kinds of mass.
Right. So, but anyway.
So you got something to show us today. Hello to everybody, by the way. Welcome to Coriolis-Effect. We're scrambling around here a little bit today.
Yes.
But we got some cool stuff.
I'm running ahead with this in spite of my ineptitude. Honestly, I'm better at writing C code than using oscilloscopes. And that says I'm really not good at using oscilloscopes. I used to do it a lot when they were all analog,
Yeah.
But this is such a beautiful instrument. Like and I only have it for a few more days, and I'm have to send it back because it is a demo unit that Keysight.
Tell us what it is. Who makes it and what is it?
It's a Keysight MXR608A. So these are the kinds of oscilloscopes you see at trade show booths at DesignCon. It's like a flagship oscilloscope. It is 8 channels. 8. And it's MXR608A. So it's mixed. So it also has a logic analyzer function, but I haven't even pulled the cables out to fiddle with that yet.
Right.
I haven't had time this week. The reason they lent me this scope is I'm working on a project and getting to know some of their stuff with them, and also needed something with 1 gigahertz bandwidth or better, which I don't personally own yet. And they said, well, you could try one of our demo units for 2 weeks and send it back to us. But this is, I feel like the guy who just got his permit barely and was handed the keys to test drive a Ferrari. This has so much in it, and I'm not able to barely scratch the surface. Unfortunately, it came with 8 probes. That's great. It's great that it came with 8 probes, but the probes are 500 megahertz probes. So we have an 8-channel scope with 500 megahertz probes. The scope itself is 6 gigahertz bandwidth on each input. 6 gigahertz.
6 gigahertz, yes.
And 16 gigasamples a second at 10-bit. Most scopes are only 8-bit, like mid-range scopes are 8-bit.
Right.
So this thing is, it's actually, you could maximize that screen there. It's actually, it's a PC. You can see it's running Windows. It's got the Infinium is the oscilloscope software that you see in the screen there. That loads on startup by default and goes full screen. But you can attach an additional monitor to it. I'm just duplicating the screen through the DisplayPort output, and we're capturing that as a camera for the stream today. So that's how I'm sharing it. But this was cool because it didn't just come with the Keysight stuff. They even have MATLAB installed on it. MATLAB release 2022B, a full license or partner license to MATLAB. And if you owned one of these scopes that basically is a Windows workstation, this one's running a 3.2 gig Core i5 quad core processor. So it's got a lot of decent processing capability for the Infinium software to do all the math and analysis and other stuff. But it just makes it super easy. There's USB ports all over it. So what I was doing was I've been doing screen captures for the contract project I'm working on for another customer, and I'm just saving them all to. I've got a USB thumb drive that's also a Wi-Fi shared drive. So if I wanted to, I can flip that on and connect to it with my phone or other devices and look at these screenshots. So it's just super convenient. It's on the network.
Right. Which is good and bad when it comes to things like viruses and whatnot. I know.
Yeah, now this one is, because it's a demo unit, they've got it somewhat locked down, so I couldn't install anything else. I was kind of hoping I could install the dual scope software on it and run it all from the oscilloscope, because for the project I'm working on, the dual scope's actually coming in handy for measuring input power to the device. But so what I'm just going to save the setup right now, because this is still currently set up for that project I was working on. I'm going to call that MXR608A. Oh, I'm hitting the wrong keyboard. That's what I kept forgetting. I'm on my desktop.
I have a keyboard for my oscilloscope, which is assigned
its own mouse and keyboard. Yeah.
I have one of those little minis that slide right under my MDO. It's very nice.
I accidentally zoomed the StreamYard, so forgive me. I'm going to hit reset, and then we're good to go. Okay.
Yeah. StreamYard still looks good.
MXR608A PN. Oh, I'm going to call it PAPC PN setup. So I can just recall the setup of all the channels and everything for my project later on when I get back to it. And then for now, what I want to do is just go ahead and
right off the bat, the ability to show 4 separate traces in 4 separate windows is something that I don't have the capability with any of my scopes. So that's an interesting feature.
Yeah. So this is just reset to factory default with channel 1 only enabled. I have it came with a bunch of probes, as I mentioned, but it also came with a very expensive looking coax cable. And I've got that hooked up to a gen output. So what I want to figure out is, oh, look, there's demos. What I want to figure out is to go to waveform generator. So it's got a built-in signal generator. This goes up to 20 megahertz maximum, I believe. Oh, again, hitting the wrong keyboard.
So Mike Fikes has asked the question, why does it use BNC? It seems like it'd be better off with SMA.
Yeah, SMAs are too small and flimsy for oscilloscopes.
And you have to revolve them all the way on rather than just a twist to click.
Exactly. I think, yeah, SMAs wear out really fast, and you have to have a nice torque wrench to get them torqued exactly right. BNCs are just designed for instrumentation and have been around for over 100 years. So I don't think people really want to change it. They could. I mean, you know, RF test gear uses N-type, which are screw-on. They're like gigantic SMAs, but there's a lot of metal in them, and they're very robust and sturdy. Yeah, let's go. Just hit max. Why can't I hit max there? Again, wrong mouse. Dang it. Okay, so it goes up to 50 megahertz. Let's see how clean the wave can be. We'll start with a square and an amplitude. Let's just do...
Give it a volt.
Okay, 1 volt. Let's go.
You gave it... There you
1 volt. Okay, and then let's go output high impedance, output load. It's going straight into a 50 ohm. Now they could be 50 ohm or 1 mega ohm.
That's cool that you can set the impedance of the generator. Most of the time, test equipment, in my experience, is 50 ohms output.
This is cool too. It's got optional modulations. I like that.
Right, right.
But for now, let's just start with simple square wave. So there it is. So that's a 50 megahertz square. The channel one's probably not set up right yet. So let me do that. Channel one. Set a 1 volt per division because we only have a 1 volt peak to peak. That's plus and minus half. I could do the basic things I can do with all dials on the front too. So that's probably faster because it's what a normal engineer who uses scopes knows, right?
Yeah, yeah.
So yeah, that's set to 200 millivolt per division. So I can cancel out of that. And I'm going to set the impedance. See, this is still high impedance input, and yet the output of the generator is set for a 50 ohm load. So I'm going to hit that. It says, please ensure the input signal does not exceed the maximum. And on the front of the scope, it says, for a 50 ohm setting, do not exceed plus or minus 5 volts. Probably because it's a very small terminator. So now terminating that with 50 ohms, yeah, I can see the voltage dropped quite significantly from the generator. And now that's set to 20 megahertz. I thought I set that to max, but okay. Oh, an amplitude, it kind of reset it. Why did it do that? So let's go to 1 volt. And let's do maximum. That's interesting. So when we were in this dialogue before, it was going to give us 50 megahertz, and it didn't. Maybe because I selected square.
You're right. Somebody suggested it can do 50 megahertz sine, but not square.
Yeah, it's got to do with they know the power output of the generator must have a certain bandwidth limit there. Yeah. Yeah, that makes perfect sense. So, but that's a really nice sine wave. Let's look at the like it looks like a perfect sine wave. Let's look at the
it looks harmonic free.
Yeah, let's look at see all these massively high powered analysis things for digital.
Yes.
Right? And I don't have the setup. I don't have
ooh, quick eye diagram. Doesn't that make you want to click on it? Just quick eye diagram.
I know.
Oh, look at those colors.
Fault Hunter.
Like, I wonder what the fault hunter
is. This is the kind of scope you need if you're going to debug a DDR4 or DDR5 interface. Let's see. New FFT is what I want though. Channel 1.
So is the 5 volt limit? You said you suspected it was due to the terminator, but is it possible? Is this thing limited to 5 or 10 volts input, unlike a garage scope?
If I go to the 1 mega ohm input impedance, it's plus or minus 40 volt max.
Okay.
And I'd say it's because the built-in termination inside the scope is only able to handle so much power. It's probably like a quarter watt resistor or something.
Right. Yeah, I noticed in Mike's recent video, his terminator had heatsink fins on it, so they come in all sizes. So you could terminate externally to get more voltage, more power.
Yeah, if you can get a higher powered terminator. So look at this. This is a really, really good sine wave. There's a little bit of additional harmonic content just above the fundamental, but there's pretty much nothing else out.
Nothing.
And just for fun, let's go back into let's go back into that generator and look at something else here. Let's go.
Right. And so Drew Dastardly just mentioned what we determined last time with the arbitrary waveform scopes is the square waves, the fundamental harmonics require more bandwidth. So we can go higher in frequency with the sine wave because we don't need any more harmonics to build up the wave. Whereas with the square wave, we need to get in several odd harmonics to get any kind of reasonable shape.
So this is a sync pulse, and it repeats, right?
Yep. And you see a little harmonics popping up down in the bottom.
And what I want to do is, so the triggering there is kind of funky. So I'll go up there, and then I'll center it on one sync pulse. So.
Oh, Mike mentioned it'll actually, on his tech scope, it'll turn off the termination if it overheats. That's cool.
Yeah, I haven't tried to hurt this one, and I don't want to.
Don't.
This oscilloscope, the list price is around $140,000.
Yes.
I'd sooner finish renovations on my house than be able to get one of these. But you know,
that's how you troubleshoot DDR4.
well, there's a point. Like these things, it's like professional orchestra musicians sometimes mortgage their houses to buy the instrument they need to play.
Right.
Some violins are $500,000 easily, even for and we've all heard the stories of auctions whereby ancient Stradivari violins go for millions of dollars. I'm not talking that. I'm talking like 20th century manufactured, but really good ones could still be $500,000. And professional musicians have to get a mortgage to get the instrument, and then they have to charge their hourly rate for their orchestra job that can pay them a living and pay for the instrument. So
have you seen what goes into some of those violins? They used to soak the wood in like a stream for 2 years to dissolve out some of the organic matter, leaving behind the celluloid. And they're trying to reproduce that now by doing things like diamond dust. You know, they're trying to figure out how to create that celluloid structure that is the sound of the old violins. I'm saying celluloid, but I mean, the leftover structure after you dissolve the organic.
I love Drew's comment. 140K, that's a tank of gas with Biden inflation. Yeah, I agree.
Yeah, let's not do politics.
It's not attributable to any one person either. It's a system.
Right. We had a pandemic. Yeah.
And it's more than that, but whatever.
It is. It's complicated, but we're talking electronics.
Yep.
Half a tank in the UK.
Half a tank in Australia too.
Yeah.
It's crazy. So yeah. That's fun.
Cool stuff.
It's fun. The sync pulse, the repetition of the sync is only 1 megahertz, but the actual sync frequency is much, much higher than that. And that's the these harmonics we're getting here. 2.4, 3.2, 4 gigahertz, and way up here at 6.4, there's a bit of harmonic action going on.
Wow.
With the sync pulse. But actually, that's noise on a sync. A sync pulse in the frequency spectrum looks like a rectangular block. And let's see if I can zoom in on that. No, I don't want to add a waveform. That's the wrong button. I should be able to zoom. See if I can. That's still the channel control. How do I zoom on the FFT? Now, this is where I'm showing my ineptitude with modern scopes.
And you know, a piece of equipment.
Yeah, I just need to set the stop. No, I don't want to stop at 8 gig. I want to stop at, let's see. 100 megahertz. So yeah, that is the sync part of the sync pulse that in an ideal FFT looks just like a square block or a rectangular block of frequencies. That's a sync pulse.
It is sync pulse from where? Tell us a little bit more about that, if you would. It's because I don't know what a sync pulse is.
It's
I mean, I know it's synchronization. Yeah, you know.
A perfect sync pulse is a non-causal thing, technically. A perfect sync pulse is the formula. I think it's what is it? I got to look it up. I'm sorry.
No, I didn't mean to get us off on the on a tangent here.
It's like sin x over x. Sync pulse.
But it's a single occurring event or an event that occurs non-repetitively, or
has time in the time domain. A proper sync pulse has content before 0 time and after 0 time, and it goes on forever before and after. Yeah, okay. It is sin. I was right. It's sin of x over x.
X, yeah.
And of course, in a signal generator, you can't have negative time. So it's a sync pulse delayed, and you can't carry it on infinitely negatively and positively in time either. Because a proper sync pulse has these sine waves asymptoting out to infinity, right?
Right.
So to have a frequency, a proper sync frequency response in the frequency domain would have a 0 time, and on either side of it, it has a flat line and then a hard wall down.
Okay.
Right.
Right.
That's impossible. So we window the sync pulse so that it doesn't asymptote off forever, and the size of the window we shift out to start at 0 time, and then it gradually gets up and then gives us the pulse and goes back to 0, and then we can repeat it. And that's what gives us the ability to measure devices that respond to something close enough to a sync pulse. It's not a true sync, but it's almost a true sync. And that's why we still have all this noise in the FFT, and we don't have a perfect right angle chop off on the frequency response down here. If you see the oscilloscope, like that should be perfectly flat, and then it drops off to infinitely 0 vertically. We don't get that because we can't have that perfect negative time in asymptotal. So yeah, Dirac. And I'm very quickly out of my depth in all this stuff because it's been too long since I've actually studied or used any of it. Most engineers past the age of 40, I think we've become a lot more practical and do things by what we know.
My tokenizer is broken. I used to put like 12 bits in a box, and now when I go and look in the box for the little piece of information, I'm only getting 7 bits out of the box. So I blow model numbers and, all these things where we compress information down to little factoids. I find when I hit 60, my compressor broke, so I'm not getting the number of bits I stored, I'm pretty sure.
This is the other thing that it came with that I haven't really played with yet. But it's very cool. But I don't have the right tips for it.
I got a couple of kits this week.
This device is an isolator.
Oh, yeah. Let me zoom in on that. Hang on.
A probe isolator.
Okay.
Right. So this does high impedance. It has the sticker is partly covering it. But if I look at the back, or if I look at the user guide for this is a high bandwidth isolator. Okay,
we can see it. Yeah,
I believe this isolator, the PP0004A, does have I think 3 gigahertz bandwidth. It may be 1, but I think it's 3 because if I looked at the user guide for this, or this is the quick start guide.
Yeah.
I think it says it's compatible with 1 gigahertz probes that are designed to go with it. So it's probably a 1 gigahertz bandwidth or above 1 gigahertz, so that it
okay.
work well with a 1 gigahertz probe. But the probe they sent with it, only for use with PP0004A. So this is the specialized probe that came with it. 30 volt RMS, 1 gigahertz, 4 picofarad, 10 mega ohm impedance.
Okay.
But the problem is this one has an MMCX connector on the end of it. I can't get that to focus. MMCX. Focus, you stupid camera.
Pull back just a bit. It's black too, so that's not helping.
Oh, I nearly had it there.
Yeah.
This type of little plug is an MMCX.
Okay.
And it's used for high-end headphones and stuff, oddly enough. But the only end piece that they sent with it is clip leads. So these are not high bandwidth. And I tried to do a compensation on this and it failed. I'll try it again just for fun. But, you know, there's a lot of inductance right there.
Yeah, yeah.
So I'm doubtful you'd measure it. Maybe they compensate for it, right? So let's try it. I'll try and get it to work. But what I really want is an MMCX to N-type, because I want to plug the output port, or I want to plug the driving port of my $2,000 handheld VNA into the scope and see what the VNA is putting out to do measurements, because I just think that would be fun. And it goes up to 6.8 gigs, so we can get beyond the bandwidth limit of this thing. So let's go. I'm going to hook this into channel 2. Just plugs right on. It's got this magical BNC thing that's really cool.
Yeah, Mike's question about BNC bandwidth actually is kind of still bouncing around in my head, because BNC kind of is limited to a couple gig. When I go on the mini circuit site, I don't see any BNC components past 2 or 3 gig.
No, and I think the instrument manufacturers have to compensate for it and do the math on the front end to counteract that bandwidth limit.
Right. And I assume it's a good BNC.
And these are incredible. Yeah. But that's probably why these probes are so pricey, you know. It's because they have to do a lot of stuff like that to get around the issues. Yeah, so let me go to set up channel 2 now. And channel 2. We're using a precision probe cable, so I'll go set up on that. Start precision probe cable AC calibration. And the probe transfer, we want to correct for probe transfer function V out over Vn, or estimate of probe system response, V out over V incident. In other words, S parameters of the probe. We can do, oh, look at this. We can store the S parameters of the probe itself.
Oh, wow.
For later use. That's pretty cool. For a constant impedance. I don't want to do that right now. So let's go back here and choose probe transfer function. As a DC calibration needs to be performed prior to the AC. A DC will be started, and when the calibration is complete, you may reinitiate AC calibration. Okay. So I've got that hooked up. Probe to cal, ground to ground, done that. This is cool. Like, the scope itself is showing me exactly what steps to go through. That is cool.
Somebody just asked about my rooster.
Oh, look at this. This showing the waveform it's using for that. Interesting.
You know, that looks as close to an analog scope as I've seen too.
Yes, the waveform display on this is super easy on the eyes. I found it's definitely bright enough. Yeah, they've got some really good display processing in here. This particular one, I guess because it's a special calibration routine. You know, it's just running through some automation here.
Yeah, no, it's like watching the auto setup on the old projection TVs. You know, you sit there and watch it do all its things.
While that's going on, I don't know how long that's going to take. Let me show you the.
It's actually done.
It failed.
Oh, it failed.
Yeah. And I think that's happening because the tip they gave me is just those little flying leads, the clip-ons. I think there's just no way it's ever going to get where it needs to go without a proper tip on it. So these are the probes that come with it. So that's the thing. You're going to spend $140K on the scope, but these are only 500 megahertz probes. So if you want 6 gigahertz bandwidth, you're then going to go out and buy several, probes that cost thousands of dollars each as well, probably.
Right.
I don't know exactly. There's so many probes available from Keysight. They probably have high bandwidth probes that are not that expensive, but either way, you're just going to be accessorizing this thing.
Now, do you have any of the, I just pulled out my probe tips for grounding, these little pieces of wire that.
Yeah, it did come with a bunch of all that kind of stuff.
Okay, cool.
And what's also useful, the probe tip adapters for BNCs. I was asking them for probe tip adapters for SMA for this other contract work I'm doing, but I've had to use the BNC probe tip adapters. I don't think they actually even make them for SMAs because I haven't ever seen any. Right. So I have to go through various adapters and they're all going to affect the signal quality. So this is a probe tip adapter for BNC. So
all right. Yep.
Right. This just goes into a BNC. It doesn't have to lock in or anything. It's a press fit. And this end, the probe tip, which is like a little spring-loaded needle, goes into that.
Okay.
And then the sleeves connect and you get a good ground shielding.
Wow. Okay.
And then, so on my handheld VNA, I've got the N-type to BNC. And that just goes straight in there. Right now, this is not terminated, so it's who knows what we're going to see here. But this is just an experiment for fun, right? Just to see.
Right. And mentally, I asked myself, now are the voltages with the VNA compatible with the scope? And I got back the answer yes in my head.
Yeah, max the peak voltage out of here is 10 volts. It won't. This thing being battery powered and all.
Okay.
They're not going to test. It's not a power amplifier output. Let's put it that way.
Right. So I think
how's my battery level?
Yeah, I was looking at my CSA. My memory is it's good for only 5 volts. It's not a scope. It's meant to look at a certain type of signal.
Right. So what I want to do.
So tell me about the VNA. I didn't. What VNA do you have there?
This is the Chinese Misol KC901V. These were reviewed in quite some depth by the Signal Path. And it was the signal path video that made me realize, no, I can get a decent VNA that's certainly adequate for what I need to do.
Okay.
For
so when did you get that?
I've had this for a couple of years.
Okay.
And it's been one of the backbones of my RF PCB design training classes that I've done at PCB West, Apex, and which will become a course which you can get online sometime.
Yes.
Soon, hopefully, right? But that's my thing, right? I put this whole RF PCB design and an RF PCB antenna design class together. They're shortened versions, but I'm going to do a more in-depth, longer version where we actually get into the CAD as well, and go from design spec to actual library of models, and that will be an online course. But I'm still working on that. It's going to take a while. But yeah, it says probe attached to channel 3. So it recognized it. They communicated. So let's go set up channel 3. I'm going to turn that FFT off because I don't think we need. Whoops. Oh yeah, it was also really convenient. Hey,
does it have a touch screen?
I touched on this, and it is not a touch screen.
Okay. I don't like touch screens.
No, I don't. I don't want to see smudgy finger mark grease.
Right. I don't want to double click and drag. I don't want to try and do all the stuff I do with the mouse.
Yeah. Okay. So I'll DC couple it. This is let's just turn it on for starters. I want to make sure bandwidth limits ought to all be off. Okay, there's a 6.3 gigahertz bandwidth limit on channel. It's like this goes up to 6 anyway, so
right.
It knows the probe capabilities. So the precision probe on channel 2 is a 1 gigahertz probe. The generic probe on channel 3 is 500 megahertz, and on channel 1 it's just going to the generator with that coax cable. So now, like a normal scope, by default it overlays these things.
Right.
I can just resize the windows. I could probably, like Altium Designer and other tools, I can unpin it or have it docked or put it on a separate monitor, because you can plug an extra monitor into this. And that was really useful yesterday as I was working all day on this scope with testing and bringing up a board that I'd reviewed. And it was super useful just having the web browser right next to it and going into the schematics and reviewing all the test points and the board design through the web browser. So, but when we started, there's all this stuff you can do on display. So let's go waveforms. We can separate them into grids or tile them. That's how I had it tiled before. Let's see if I can generate something here. So let's go. I'm going to go center frequency 2.45 gigahertz. And span, full span. So I guess it's just sending pulses out. I'm going to have to look at triggering. We'll do a one-shot trigger on channel. And it's honestly easier to do this using the mouse. Let's go trigger, setup. I don't want to trigger on channel 1. I'm going to trigger on channel 3 now. Okay. Function.
I'm sitting here thinking of the power of a scope that has MATLAB running on it.
Oh, yeah. And automation. So here's the other thing. All this software can be scripted and automated. So if you have to go through a series of very complicated tests for a complicated product, you can figure out what you need to do, go through it manually, but then basically write a macro to automate that process over and over again. And that can also involve driving MATLAB behind it and post-processing the data.
Right.
Every waveform can be saved. You can save screenshots. You can export the actual capture points, like everything. So I've really got to learn how to use this damn thing. So I go to the function menu, but now it looks like I'm in something like preferences or setup. Sweep points, 450, sweep speed, medium. And exit that menu. Maybe I should go into the port 2. But it's port 1 that gives me the S11, and so that's where the source should be. Run.
In a VNA, a vector network analyzer, is basically a sweepable RF transmitter with an RF receiver built also. A pair of RF receivers. It can receive on the same port it sends, and it can receive on port 2. So it can see how much signal made it from port 1 to 2, or it can look at the amount of signal got reflected back to port 1. And there are micro VNAs available. They're not as good as the big ones, but I've got one around here somewhere I can drag out. And then I also have a Tektronix 6 gigahertz R360 or something. 306B. Or is that my
mode?
That's my analyzer, sorry.
Yes.
So yes, I have a TTR 500 series vector network analyzer from Tektronix.
RF source.
Now, have you ever...
it's going out on port 2.
Go ahead.
Let me go to switch the other port. So this VNA I can use as an RF signal generator as well, which you would expect. You should be able to do that. Gosh, that's stiff. Okay, and I can modulate as well. So let's go port 2.
Here's a micro VNA.
Type FM.
The nano VNA. So I imagine some of our viewers had the nano VNA. I know people like Mike Fikes has something similar. Yeah, here we go. Tosca saw Alan Wolke with his nano VNA. Yeah, if it's good for Alan, it's good for us. Yeah, that's a fair enough statement. Though I think Alan talked about the shortcomings, just so you're aware of them. And I believe the shortcomings are mathematical. Coming from a guy that doesn't know math. Me.
I'm probably hitting a bandwidth limit here as well.
So Fred is asking, who would be the biggest, most obvious customers routinely using 140K to 200K scopes? And that's an excellent question. Certification, government labs, independent testing. You've mentioned DDR4, DDR5 testing. I can see it in automation. I don't know if you'd use it as automation in a production environment, but certainly in characterization. I'd almost bet that if you have to ask how much the scope is, you can't afford it. That old line.
Of course.
So, and again, you know, as a smaller time, I've worked for big engineering houses, as you may know, but for, you know, for the smaller houses, there is equipment rental. I'll throw that out there. That some of this equipment is available. I'm not saying it's cheap, but it's not 140,000, but it might cost you 1,000 a month. But to a business that that needs that as a business deduction, it is available. So rental is one of those things.
Yeah, I don't know.
Defense contractors.
Oh, there it is. I forgot to hit stop run. Ooh, it's a square wave and not a very good one. So this is my KC901V. Let's just maximize that.
Yeah, I want to see you throw that into a FFT now and see if we see that harmonic causing the not very good square wave.
Yeah, I'm just going to disable channel 1 for a second here.
So my tech scope is half front panel, you know, it still has half the controls on the front panel and then menu-based system. This system here, they literally have taken all the controls off the front panel for the most part, I'm assuming.
Well, all the basic ones are here, and if you really had to, you can get around everything here.
Okay.
But configuring the display windows like this FFT. Oh, come on. There it is. I don't want that menu.
There you go. There's your harmonics giving you the saddle.
And let me turn FFT. How do I disable this one? I want to turn that off. Yeah, that's right. Let's close that one. There it is.
That's pretty cool.
And that's only, excuse me, that's only a 150 megahertz. Right?
Right. Okay.
Let's go to.
Yeah, I remember when 150 megahertz was so.
Oh, wait a second. This is probably also modulated. Let me.
Yeah.
Turn off.
Oh, I assume it's supposed to look like what you're looking at, kind of.
So there's no modulation. I could just set the modulation depth to 0 and go run. No, that's even without modulation.
Okay. Okay.
It's still not very good. So, you know, this 250 megahertz looks closer to. Oh, now, on the other hand, this is probably also reflections because I'm not terminating.
Oh, terminate it. Terminate it. That would be
terminate the channel. So let's do that and see what happens. Terminate. Yeah. Let's go channel 3. Cal trigger.
Right there.
Grayed out. It's grayed out. I don't know why.
Are you on one of the upper? What channel are you on?
Channel.
Whoop, we lost you.
Am I back?
You are back. Keysight Labs just asked, how's it going?
Aha. It's a lot of fun. This is a really great instrument. But I feel like I barely just learned how to drive, and I've been given the keys to a Ferrari for a test drive on the track. So yeah, I don't know why, but the impedance is the selection there is grayed out. Maybe it's not possible for this probe. And so I should probably use a terminator. So let's see if that makes any difference. I'm going to disconnect the probe. I have a 50 ohm terminator here.
Well, once you disconnect the probe and you're on a BNC, is 50 ohms available?
Well, I just put a BNC terminator right on the output of
very good.
VNA, because the probe is a high impedance probe.
Right.
Didn't really make any difference. It did modify the amplitude a little, but it still really looks like a square wave to me. That's 50 megahertz. 250 is more like 350 is more like a sine wave. Let's stick to that for now, and I'll add some modulation to this. Let's do some FM modulation deviation, 10 kilohertz, and modulation frequency. So that's the other. Yeah, I'm not even hardly seeing that in the FFT.
Well, I'm wondering if we can bring Keysight Labs in. Is there a way to get the link for StreamYard to Keysight Labs? Do you want to join us here?
We could send.
I've got the link. I just don't know the. I can post it here, but.
Let's do some ASK.
Let's see. I think I can do a private chat here. Private chat.
So you can see the amplitude shift keying kicking in there in the waveform on the top. And then if I compress that, we'll see. You can see the amplitude shift keying going on there. Modulation depth only goes up to 90%. Trigger level.
So what are we looking at now?
This is an amplitude shift keyed. And this is the kind of thing, if you want to see the modulation, just like when you're looking at TV waveforms and other stuff.
Right.
This is where you want to go into your trigger settings and modify like hold offs and siege.
Now, can this do like quadrature amplitude modulation, demodulation? Can it do QAM and?
No, I wish it could. That's the difference between a low-cost instrument and a proper bench RF signal generator. An RF signal generator is going to give you all those different things.
But the scope, can it demodulate QAM?
I have no idea. I would say probably not. I don't think it's really targeting that. So yeah, we could do HF reject or low frequency reject. HF reject is where that was originally put in analog scopes back in the day for TV. So it wouldn't trigger off of color modulation or anything like that. It would just look for the back porch or the front porch. Yeah. It appears to be triggering better just without changing any of those things. And again, I'm actually somewhat inept at all of this, but that's ASK.
So Keysight Labs has said that QAM can be done in VSA software. So I'm not sure what VSA software is. I don't know if that's an add-on or something that resides on the scope.
It's probably, it says Connection Expert, Keysight Instrument Drivers.
There's VSA.
Manager. There it is. Yep. Vector Signal Analyzer. So this scope, it basically is just the front end for sampling stuff at a very high sampling rate and high bandwidth. So we'll see what happens. I don't know if I can run this Infinium app and the VSA app at the same time, but we'll try. I'm not seeing it. Maybe it's not licensed on this version. Oh, here he is. Hi,
Hello.
Daniel. Thanks for joining us.
Hello. How are you?
This is
I'm
the
doing
expert.
well.
This is the expert. Okay, VSA is running. It takes a while to boot.
I'll add the caveat. I haven't had much stick time on this specific scope, but my background is scopes, and I've played around with them quite a bit. So
my stick time on this is literally two working days, so it's nowhere near enough.
Yeah, we can work through it together.
This is
so
fun.
VSA it's a cool software. It runs using a lot of the technology from our RF products as well. So this is how we do we can do a lot of 5G measurements this way, especially with our high end, like the UXR 110 gigahertz scopes. They'll do those millimeter wave. They do they call it the millimeter wave extension, where you can take like a bandwidth swatch and you get rid of all the DC. And I posted a short on the labs channel a couple months ago from IMS, where they were doing 307 gigahertz 6G research signal.
That's insane.
Yeah, and you basically use the scope as a the scope as the capturing end, and you can demod and see the whole thing. It's super cool.
Yeah, this thing is super impressive. It's a scope front end with an acquisition and a system behind it. I assume, can this do like a Bode plot? Could you tell it enough about it that it could say, sure, here's a Bode for you for channel 1 and channel 2 relative to each other?
Yes. I know we have that on the Infinivision scopes, which is like when it's not running a Windows interface like this. We call it frequency response analysis is what you would be looking for.
Okay. Right.
I have to check the user's guide. Even when I used to be the technical support engineer for oscilloscopes, and I would just always have the user's guides all opened up and just they document it so well. Yeah.
So we got asked who would buy this scope, and we threw out some good, but you just said 5G and stuff. What are some of the technologies that would really benefit from a scope like this?
Yeah, so the MXR, which is this one of the big ones, having 8 channels, that's really pretty big for power. Just from the get-go, being able to do 3-phase like current voltage and do that 3 times is really nice for power.
So you need at least 6 channels for that, right? And that's where these isolation modules come in handy too, because you could be measuring across.
So that's a big one. Power. Obviously, the speed is that's pretty fast for a power signal. We see a lot of like compliance testing, and then a little bit of like signal integrity type work. So if you're just doing, I would call it medium speed serial. So I wouldn't necessarily call it like high speed digital signals. But if you have, I'm not sure what protocols we're doing with this one specifically.
Well, this I don't know about so the VSA is obviously for RF and the spectrum analysis, right? But this Infinium, all these analysis items on the menu, like phase noise, jitter, eye diagrams, this all points to me to signal integrity for high-speed serial when I say high
Yeah.
speed, I mean like under 6 gigahertz, but still up there. Like
SDI or something.
And
Right.
it seems like, I think, what did I see in there? I saw, I did see protocol decode. That's cool. I think that's probably for the logic analyzer input mainly, but
you know, yeah, a lot of people will just do that right on the analog channels, especially if you have 8 channels and you're just doing kind of standard type stuff. I'm trying to pull up the web page for it, and the easiest way to figure that. So automotive is a big one too that I'm being reminded of.
Okay.
There's automotive protocols, and then there's also a bunch of automotive specific measurements that, like, if you're testing car systems, that becomes
like 461
really
type.
Yeah. I think we do a lot of CAN-LIN, and then CENT for sensors.
Okay.
Our protocol buses. Those are also a little lower speed, so you don't necessarily need full 6 gigahertz. But I think in a lot of cases here, people are not necessarily buying the 6 gig version. That, like, it goes down to 500 megahertz. So
right, yeah.
when you get a demo scope like Ben got, you get all the options turned on, and it's
Right,
just like
right.
the biggest crazy thing.
It's
But a lot of people are
mind-blowing.
buying a 1 gig version. You know, that's
of course,
that's totally normal. Yeah,
that's exactly. If you go to test drive a Ford Mark E, they're gonna have the one that everyone test drives. This is a fully optioned.
Yeah,
because it's psychologically difficult to get anything less than what you've tasted.
Yeah.
Right.
Yeah.
Well, why would you show off less than you have, right? Like that.
Well, is that true? Like, that's just logical.
Yeah.
I like this though because it's got these. I haven't had time to explore any of this, but de-embedding, built in. That's a big deal. And just for those who who were wondering, de-embedding is like the probe, the test fixture, the jigs, all the stuff up to the actual device you're trying to measure adds crap
Right.
to what you see and what you capture. And de-embedding measures all the crap on its own first and then subtracts it.
Right.
That's just one way. There's other ways as well. And with it, like, Bill, you've done a lot with your TDR and reflections on circuit board traces and such. You can actually de-embed just by
cut out those
counting the time or distance up to the point of interest, and anything before that is weird. But it's like, well, there's a via there, and there's a connector here, but we can ignore those because we're looking from this point of time on.
Right. Yeah. That would blow my mind. I'm not a math wonk, but if you can, in the time domain, remove the nonlinear effects to get into the part you are trying to measure, it's like, well, wait a minute. I know how to subtract out time, but and so my memory is it involves a lot of matrix math in the T domain. I can't remember how to de-embed.
Yeah, it's a lot of like scattering parameters. So S parameters, and then if you get to the higher end, it's X parameters, because they have to, make it fancier. Even like the probes, when we build the high-speed probes, we do automatic characterization of all the probes with a VNA and load those profiles into the probe itself. And then when you plug it into the scope, it loads those profiles and de-embed probe effects based on that specific probe. So you just kind of extend that capability out to whatever fixturing you have. And it's all that RF, big brain stuff that I don't fully comprehend either, but it's a big matrix of S parameters, like you said. Yeah.
Right. Well, you just said that the probe is smarter than a Commodore 64. That's what I heard.
Pretty much. Yeah.
Well, that's what we're looking at here too, is some of that stuff. So, and you'll see menus and dialogues like this in the high-end simulators too, like Keysight ADS, Pathwave Memory Designer, and other add-ons have these. So I'm looking at equalization, channel equalization, which is a big deal for it is mainly used in DDR interfaces, right? To get the memory bandwidth we want to use now. So what we're looking at here, that's that formula, and anyone who's studied formal engineering would recognize this is a it's a transfer function of a channel, right? Or in this case, it's the transfer function of the equalization that's going to be applied to the channel. So here's the problem. Equalization's done in the silicon, and we can't probe inside the silicon. So the silicon manufacturers like Micron work with companies like Keysight and give them models of what's inside their silicon. And then that can be bundled not just in the simulation software, but in the scope. And that way we can use their chip, but measure the pins just outside the chip. And if we've done everything else equal to what we simulated, then we can measure it, and the measurement results will look the same, because the scope fills in what comes after the pin to the actual memory cell. So,
and also, say you're testing a transmitter, right? So you have your transmitter, and you're wanting to see how good your transmitter is performing. Your scope essentially needs to act as a receiver, and like you're saying, the receiver is going to have this handshake and this equalization, filter taps happening to make sure that it's adjusting that input signal to optimize and receive it as best as possible. So the oscilloscope has to also have that capability, and that's where, like number of pulls, like how many taps are you putting in your receiver to make sure you're opening that eye up high enough. And
that's that for those who haven't looked at DDR5, for example, that's what Daniel's referring to, decision feedback equalization. It's a type of almost an impulse response filter, but it's sampled only at the clock rate, rising falling clock of DDR. But what it's to compensate for intersymbol interference, right? Am I getting this right, Daniel? Yeah.
That is my
basically if I have 2 1s in a row coming down the PCB trace to the DDR chip, they set a bias basically at the pad of the chip. Those 2 1s in a row have there's capacitance on the board, so it takes a while for the next 0 past the 2 1s to actually get to 0. And we're going too fast for all of that. So the waveform is falling with a decaying exponential. And what DFE does is it says, well, the last 2 things were 1, so I know there's a bias for capacitance.
Right.
So we compensate for that by feeding back the last 2 bits with a special summing circuit to the input pin or the receiver, and that compensates or pushes down the signal unless it's another one coming in, right? So it makes a decision. Do we add or subtract based on what's just come in before? That's why it's called decision feedback. And the number of taps you have, it slows down or adds latency to the reception of the signal, but it makes it more accurate. Or you can reduce the number of taps and have faster reception, but you might get more errors every few billion bits.
Right.
You don't need me.
Almost
You got
like
this covered.
pipelining.
What's that?
Yeah, go ahead. Sorry. I said, you don't need me here. You got this covered, Ben.
No, the problem is I can't show it. I understand it. I just can't. I don't know how to drive the scope, and I don't have a DDR board to hook into it to show people. That would be the next thing. I need some kind of demo set up.
You can look at that demos tab on the top, and I don't know if you've been in there yet.
No, I did see that.
Yeah. So you can actually walk through. There's a long list of demos here, and we have. It's not live signals, but it's preloaded in. So
let's see a demo.
Actually thinks,
like that. So let's do some.
So power rails, like you saw there, power rails another big one that we see people like bringing up PMix and that sort of thing to make sure it.
Okay, so where would I find the power? Would it be in other?
There's probably a power window. If you on the left side, if you scroll up.
UI, MSO, more instruments.
I thought I saw it under RF. There was something that was like FFT on power rail noise.
Yep. Oh yeah.
Wow.
That's interesting. Look at that.
And then in the right, you hit load demo. Like in the top right there.
Bang. Okay, and this runs a little like plays back.
It should run natively, so it's gonna it's basically running. It loads those points into memory as if they were acquired, and you can kind of.
Oh,
my
that's
understanding
awesome.
is make measurements and everything on it. Yeah, it'll set it up for you.
The FIR filter will be applied to the next acquisition. Cool.
Yeah, that's cool.
So you can see, you have your main capture of your power rail, which I assume is that green channel, or the math. Oh, function 2.
This one here.
You have a couple math channels, a couple Oh yeah, okay. So you have channel 1 is that very top row.
Yep.
And then channel 2 is the zoomed in version of that.
Right.
Same thing, row 3, and that is an acquisition.
Okay.
And it looks like these are loaded into math channels, so you can basically take a capture and then save it as a reference or math channel and treat it just like a normal channel. And then the bottom is going to be an FFT of something.
That's the FFT that's looking at F1. So F1 is
so F1, that's function 1. So that's its own. That's probably an FFT of that math 1 channel.
Oh, I see.
If I had to guess, or 1 or 2. It kind of looks like the FFT of a square wave, so it might be the FFT of channel 2 here.
Yeah, that's what I'm guessing there. Okay, so it's just like that's a capture that was saved and it's recalled, right?
Correct. So
and there's probably some document online that walks through the setup and what they measured.
I think the demo is only available on demo units. So normally it's for a sales, sales engineer to go in, or a marketer to go in and demo it.
Right.
I'm willing to bet that that's an FFT of that second green trace, and it's showing the effect of a nearby clock signal on that power rail.
Oh, okay. Mm-hmm. Yeah. Because I can see crosstalk noise on that second trace. That's really clear.
So you if you have really good signal integrity, if you can really see accurately what that power rail looks like, then you run an FFT on it, and you can see all the signals on your board that are influencing your power rails just by looking at the FFT, because you can see what frequencies are present.
Oh, this is cool too. Like DDR3, this load demo is this oscilloscope does not have high enough bandwidth.
So
the channels.
This interface is the same interface for this is like the lowest end model that runs this interface currently. And this
I got it. This is just talking about the logic analyzer port though. That's why, right? Because these ports
MSO
have
channels
plenty bandwidth for memory. Protocol. I want to find if there's there it is. That's the same one, but I wanted to look for something like PAM4. Let's see, what have we got here? Mixed signals. So that's some kind of A to D or D to A sine wave.
Yeah, it looks like one of those two.
Oh, it does have spectrum.
It has RTSA, so that's another one that's really big on the scope. We're pretty proud of the real-time spectrum analysis capabilities.
How many programmers did it take to make the scope?
Okay, I've done this. I've got this hooked up already. So this is actually going to drive the signal generator.
I'm guessing at least 100.
Channel 1.
The team is pretty large. There's an ongoing, so there's like a software side, which the code base for this is, 9 figures in terms of lines. It's 1 million plus lines of code for this user interface, and that's just the software that runs on top of the hardware. Right. There's the ASIC team here in Colorado Springs. They they design the chips and then hand it across the hallway to the R&D team that implement it on the board. And it's a crew. Yeah, we have
Yeah, I'll
a
bet.
few hundred people site here. And then R&D teams all over the place.
I like this. It's
Look
got a
at that.
PRBS generator in
That
it.
is beautiful.
Look at that. That's lovely. So that's a pseudo-random bit sequence. And I think these spikes indicate... So wait, the fundamental should be the actual fundamental bit period, the frequency of the fundamental bit period, right? But then I wonder what these spikes mean. Maybe
sure
have something to do with
the... can tell you.
Yeah. Yes. Thank you, Fred. I agree.
Yeah. They look periodic too, almost, right?
Yeah, they definitely do.
It's like 41 and 82, or just under that.
So I can add markers to that, right?
Yeah.
So let's go to. I don't want to do manual.
Yeah, so the source will be probably that math function. This is one where I haven't had a ton of opportunity to play with this feature either.
Add waveforms, expand collapse.
It would be markers. So you go to measure mark.
Yeah.
Add marker.
Yep.
And then from there, manual X only should work. So from there, you just hit.
Oh yeah.
You can hit apply or OK.
And then just move them where I want them.
Yeah.
Right to. That's it.
So M2's at 39.9 megahertz.
I like things in proper order here, so let's do it.
Yeah.
I love that they added these little call outs on top. I've been trying to get them to implement that on the
these things. Absolutely.
Yeah. Trying to get that on the Infinivision too. I think that would be really useful. Or they maybe have added it. Not sure.
How do I? So okay. It looks like this is where I set up what kind of display I want to do. Because channel 1 is currently set up as spectrum analyzer, but
so you can go to Windows on that first leftmost. Oh, right where you were. Display setup, and then Windows is the leftmost tab.
Yep.
And then from there, you should be maybe add, or maybe it's under waveforms. There's somewhere you can add a window. And
well, I can.
It's under display for. It's under. It's almost certainly in display. You may be able to just right-click the screen too. I'm not sure. That looks.
This is channel 1's currently on. Handing window. Acquisition hardware. I like that I can change the actual window function of the input. That's interesting. Acquisition waveform generator bandwidth limit.
It's almost certainly under that display, and there's a way to add another window here.
Source view. Appearance.
Let's just work through it.
Results.
Try. Yeah, let's look under Windows again real quick. Cause Oh no. Okay. Try right-clicking the screen possibly, and just seeing if that lets you add a window. Like close that out and just right-click in there. What number of grids?
Layout.
There we go. Number of grids there, and you can do 2. And now from there you can
separate number of grids, waveform window, layout, waveforms.
Yep, and then we want to select grid 2. Yeah, right click that. There's a way to assign try waveform. Try separate into grids and see what happens. That may give us both.
That's
or
what
that
we
may
have
just,
right now.
Okay.
Um,
You're trying to see channel 1 in real time as well, right? Like in the time
yeah,
domain?
I think I'm going to set up channel 1.
Oh, there you go.
It might depend, like I'm in this waveform view, and then I'm going to set up channel 1.
I'm going to assume it can do both at the same time, but I haven't, because that's in...
It may not be able to.
It's possible it goes through a different signal path and doesn't do both. I would have to check.
Utilities.
No, utilities is like, yeah.
Measure, display, setup. The menus actually got simpler when I went to this real-time spectrum analyzer mode.
Yeah, it may be limited. I'm not sure.
Oh, actually, look at this. Look at the top. It's RTSA. I have to switch between them.
I'm pretty certain if you had a second channel, like you could potentially double probe it and do it that way. I'm not sure how the architecture works to run both simultaneously.
So let's do a single. We'll do stop single. That's a pseudo random bit sequence, people. So we use these to test digital channels with what appears to be real data, but is just generated.
Right. I assume you're like me, that it's almost impossible to say the word random without pseudo in front of it if it's a digital origin in nature.
Right, right. So here, this is why all the menus changed quite a lot. So here I want to do...
Oh, I love the menus.
Crosstalk is pretty cool too. So if you have two channels next to each other talking, and there's a demo in there too, I believe, if you pull that
I love that. The signal is the victim. That says it all right there. Yeah.
So crosstalk would be...
Probably under protocol, if I had to guess, but maybe not.
We've got jitter, analysis, bursty waveforms, equalization. That's something that again comes
we do
back
get to see some. Hey, so Ben, there's kind of the answer to my question earlier. Is how can we show a eye diagram? And the answer is it's built in.
And we do like 750,000 UI per second on this or something. They did some magic in the hardware to just...
This is a real one coming from the generator. So the PRBS is now coming back. It's coming out. And yeah, on the scope side, we've got... So this is using the ultra expensive, really nice coax cable that came with the scope. It'd be interesting to see the effect of using a cheap, janky coax cable. So I'm going to go grab one.
Love it.
And you guys banter on while I'm going over to my cable.
All right. So, Daniel, if I wanted to marry one of these, what kind of laws of nature would that violate? I mean, I assume it violates the laws of man and God.
Well, you could. The nice thing is you can adopt them for the low price of whatever it ends up being. I don't know.
Yeah. See a little sign along there, this adopted by, like along the highway. Or you get to visit it virtually 15 minutes a year or something, depending on how much you buy into, how much you chipped in.
So nice weekends if you work at the right company. Yeah.
Right.
So this is generic RG58 and generic BNCs. Nowhere near as fancy as this blue cable.
I'm trying to think of a way to crap that signal up good in just a few seconds.
Bad adapter will do it, or a bad cable, or
yeah. Well, I'm thinking about telling him to stick a razor blade through his coax. That
looks pretty good, actually.
Yeah, I was afraid it wouldn't look that bad. Yeah.
Except I'm pretty sure that the bandwidth of the PRBS coming out it's not a really high speed PRBS, right?
You could measure it. You could do a measurement on the eye height specifically and get a quantifiable version of it.
Do you have a T adapter? Can you actually get your finger on the signal and be the bad influence yourself? I'm a big finger injector for noise, and
Look at all
It
these
may be,
measurements.
you may have to scroll down, Ben, on the measurement options. Pam might do it.
Oh,
Eye height.
Eye height. There we go. And then you just hit apply. It'll pop it in there.
The thing is, I think it's measuring it from this one. It probably doesn't matter. It'll get it the same either way, though, right?
I'm pretty sure it's on the eye diagram itself.
Okay.
I don't know, because it would have to construct the eye to make that measurement.
right.
Gotcha. And there's probably other, like we could probably add, let's see.
Yeah, if you go into the settings for that one, you can either probably right click it or double click it, if I had to guess.
Set up
like the actual measurement itself.
Now, this is displaying the size of the eye, which will tell us the errors we could expect. Does this do post-calculation where it would tell us a bit error rate or a quality signal?
Yeah, so jitter analysis is kind of the blanket term for that.
Okay.
What the eye height tells you, and usually in a spec, so if you're looking at a DDR spec, for example, they're going to say your eyes have to be this big. They have to be this tall. They have to be this wide. Right. And that's the window where you sample is this bit a 1 or a 0. So really what you're trying to do is compare your eye height to what your design requirements are.
Right.
Is my eye big enough to match? So eye is just like, is my sample region, like thresholds, do they look okay?
Right.
From there, yeah, you can do a bunch of jitter analysis, like bathtub plots and that sort of thing. You can even do jitter deconstruction, I think they call it, where you basically say which of these are inherent in just the temperatures we're using versus, recurring versus random and then there's a whole tree of jitter factors that feed into jitter.
Right. So I saw Lee Ritchie talk at one time, and he talked about on a differential signal not running them side by side, if I got that right. And his point was that you didn't want the same noise impulse on both the rising and falling edge, that the eye is really an edge detector, in spite of us talking about the size of the eye and the size of the opening, and that having glitches on both signals, you'd rather have non-related glitches than two glitches right as they're trying to cross each other.
Yeah, and you'll see this with crosstalk, where the eye will come up and then it'll kind of jog a little bit, like where something else is hitting it on the board. This is why power rail integrity matters so much, because it shows up directly in the eye.
Everywhere, yeah.
It's crazy, yeah.
So this is very cool. I think I want to marry this now that I've seen the demo mode of it.
This is just such a, I should have consulted you before our stream, Daniel, but I'm like,
no, it's okay.
You know what?
I love it. Just, that's how we learn, right? That's how I learn is I put myself on a camera and go, that didn't work like I thought it did. That's the magic of it.
It is.
Yeah. We saw Ben licking the screen earlier. It was disturbing, but comforting at the same time. It was. So very cool. Very cool.
The other one that's real cool on the scope, and I'm sure there's a demo, I'm not sure where it is. They built in a tool we call Fault Hunter, which is a machine. It'll look through your capture and basically say, hey, this looks out of the ordinary. So it's like a machine learning algorithm.
Indicator or something, rut finder.
I looked at 300 of these and they were all within 5%. But this one, I like that.
It's very cool.
That is very cool.
So, I do a little bit of network security on the side, and my only complaint about these kind of scopes is the OS is frozen in time. And OSs need to continuously be upgraded. Windows OSs, I should say, do need a little care along the years, to keep them. And I know somebody that bought a tech scope and it came infected, and it's like, good thing he didn't plug it into his network.
Well, actually, that's an interesting question too, because I've been very tempted to buy some pretty decent instruments off of eBay in the last 12 months. And generally, once they get into my price range, it means they're running Windows 98 or NT or something. Like they're running, or at the absolute latest, I've seen some running Windows XP, and it's like, what if the software that it needs and the drivers, like, where can I get that stuff to make sure I can rebuild this? And could I actually install the 32-bit Windows 10 and install the same drivers and software on it? There's probably hoops you could jump through, but I'd be concerned that I would brick it in the process.
Right.
Yeah, we don't. Once a instance of Windows goes end of life and end of support, like, from the Keysight perspective, we're obviously not on that anymore, and we're always looking ahead. But when you're picking up old parts off of eBay, it might be worth quarantining that and not putting it on your big corporate network or anything that's sensitive. That's for sure.
Yeah. Here it was Mike that he had an NT2K and had to rebuild it from the NT beginning.
No.
So very cool.
Brutal.
So what's your favorite part, Daniel, of this scope? What would you say this scope is like excels at, or is mystical, or has fixed a problem that you said, man, that scope came through for me, or that measurement came through?
Well, I think so. I'm in a weird situation in that I can, I live 10 minutes from the office. I go hop in and I can put my hands on any scope I can dream of. Right. So for me, when I'm plugging away at home, typically I'm just using like a 3000T, but I'm just doing like small embedded stuff. So a little, touchscreen embedded OS. But when you're actually getting into these things where the situations where the bugs are harder to find and the design flaws are harder to catch, having 8 channels is amazing, because I'm a sucker for just hooking everything up, and when you need it, like, oh yeah, it's already there. Great.
That's also super beneficial for scientific research. I've discovered.
Yeah.
The more you can measure at once, like, even if you're not sure you need to measure it, but I find often if it's more of a research project, I want to measure a bunch of different things around the circuit, capture it, and then change one thing, capture, change one thing, capture, change one thing, capture, and build a table of results. And later on, things may come out of that data that are interesting.
Yeah.
So
interesting. Yeah. So quantity of channels for me is really, really nice to have. And we see that like in high-end physics, they always, we can chain multiple boxes together. I've seen racks of 100 gigahertz oscilloscopes that go into optics research institutions to measure, as many different, parts of the fiber as they can. That's a really rough way of putting it.
Okay.
That's essentially how that
well, I was thinking about the price of the price of the probes. And so if I use the marriage analogy, the marriage to the box, but the probes are the children and each need a college education.
Yeah. High-end probes are not cheap. And then when you get to like 110, you're dealing with 1 millimeter connector ports, which are incredibly sensitive and fragile, and just the adapters and the cabling gets really expensive. So,
So we started off the conversation talking about the BNC connectors, and somebody mentioned, Mike mentioned in the chat room, well, isn't BNC itself limited by technology to 2 or 3 gig? And we didn't have an answer other than they're probably really good BNC connectors.
Yeah, so we use a very high-end BNC. We call them precision BNC connectors.
Right, somebody mentioned that. Yep.
Yeah, they're like super, precision milled, I think is how they're made. So they do go up to 6 gigahertz. We wouldn't put them on the scope any higher than that. But they can go up to that range with a bit of headroom. One thing I've found is on the Keysight side, our engineers are really pretty anal about making sure they have headroom everywhere, which is it's great. I love it.
Somebody asked me yesterday when I was waxing lyrical over the beauty of this instrument, and I was working with a couple of guys yesterday here in my lab on the other side of the wall, and they're like, so you could make your own. And I'm like, I do not want to become a metrology engineer. That's
right. First off, it sounds like you're into the weather,
It's one of the hardest things to do. And just think about this, like, how do you measure something that no one's been able to measure before?
Right.
And know that you're measuring it right.
Right. These are like real physics, science.
Physics
problems. Yeah.
Yes.
Yeah.
And that's why we have one of our Cal labs is in Loveland, Colorado, and it's just right down the road from NIST.
Like how do you calibrate something that's just beyond anything else that's been done before? Like, how do you know the calibration?
It's physics. So you look at like a Josephson junction, it gives you 10 volts if you build it the right way, and that's a quantized 10 volts down to the electron. So like it. Yeah.
Isn't the NIST standard based on 1 volt? They have a 1 ohm or 1 volt or something, and from there you can derive everything.
Yeah. So there's the core SI units. There's like 7 of them, and it's like lumens, and I think volts or amperes is probably. I think it's like electron flow per second, something like that. But
it's coulombs per second. Yeah.
Yeah. So I think. In the practical world, you derive it from a Josephson junction, which is the de facto standard for voltage.
Okay, yeah.
We actually had the first ever commercially available Josephson junction, and it's still in operation up in Loveland.
Wow. That's cool.
Back in like the 80s, I think, or 70s.
Yeah. Mark says still sort of principles.
It's cool. It's cool physics. It's like superconductor physics and quantization levels. Yeah.
Right.
That is.
Very cool.
This last thing, I'm actually going to have to jump off. We're over an hour and a half in, which I didn't expect. That's wonderful. But credit to Mark Hughes. I've been using these things. These were developed for camera use, but Mark Hughes sent me these.
Yeah, hold that up again.
It's a camera holder arm. This is one of the best inventions of all time. You loosen the middle and the whole thing can move. And these are all ball joints.
I have about 5 of those around here.
These are
that's how I do all my papers. Yes.
And this, Mark made these. He 3D printed these with insert nuts. That's just 3D printed to the standard camera. I think that's a 5/8 or something. Whatever cameras use.
Yeah, quarter-inch course, something like that.
And the other end goes on a heavy cheese board, which is what optics people use for laser experiments and so on, where there's 1 inch or 1.5 inch precision spaced threaded holes. And then there's a 3D printed jig the board goes onto, and then the crow probes go into these, and I can have them fixed. And even just with the probe tips with the little spring loaded ground, we have on our boards, we always use for the high speed signals, we're using a test point component that has the ground and the
little collar
and the pad, and there's little via-sized holes in the center which the probe tip can center into, and everything gets clamped down, and it's just perfect. So thank you, Mark. Excellent. And I should have thought of using these earlier.
It's better than what I saw on Twitter the other day, which was just a clothespin around the probe.
Yikes.
Right. Very cool. Well, thank you for joining us, Daniel.
I could go on about all this all day. I've got people coming to my office to work with me again in 20 minutes, and I need to zip down and ship off a guitar I sold on Reverb to FedEx. So I'm running out of time. But Daniel, thank you so much for jumping on. We'll have you on again. This has been fun.
Yeah, I'm down. Sounds
very cool. Very cool.
Always, as always, great to see you. I hope you are doing well.
Yeah, Ben should get one of those permanently. I just want to go on the record to say that you would get your marketing dollars out of it.
Sounds good. We're working on it. Yeah.
Very cool.
I agree.
So very cool. So Ben, great to see you. Daniel, great meeting you. Everybody that's still with us, great having you with us. And have a happy and a safe weekend. And we'll see everybody, if not next Friday, the Friday after.
Next Friday is Black Friday. How does
I was thinking that might be a fun day. Yeah, we had a lot of fun on New Year's Eve was a Friday last year, and we had a great time.
Right.
So excellent. We'll see everybody later.
Okay. See you guys. Have a great weekend.